Welcome back to GISC 126, Fundamentals of GIS. So today's video lecture is going to focus on cartography, data visualization, and different types of maps. So on that note, let's jump right in. So cartography is the study of making maps. So it's a combination of scientific and artistic elements. And so cartography, or map making, is the application of image processing, data capture, data manipulation, and visual display. So the question is, why should anyone care if a map is beautiful? And so an aesthetically pleasing map is a map that people will notice and then learn something from. If you aren't into making it look good, don't try at all. And so what this is trying to say is that if you spend a lot of time doing data analysis, acquiring data, and then you make a map that is poorly designed, people aren't going to pay attention to it, so you're not going to communicate your message. And if it's not done well or properly, people might think the data that's behind the map is not valid as well. So if you're going to make a map, make it beautiful. So what does it take to make a map beautiful? So contrary to popular belief, a beautiful map is not born, but made. It is not something extra human feat, but a very earthly medley of effort and experience that makes that map beautiful. So, in short, let's make some beautiful, awesome maps. So, here are some cartographer codes of ethics we'll go through quickly. Always have a straightforward agenda and have a defining purpose or goal for each map. So before you start making a map, or even the project of data analysis, you need to have a purpose or a goal. Always strive to know your audience. So when you're making a map, is the map for a city council meeting where people might have only a broad or general understanding of what's being presented? Or are you presenting a map to a scientific journal where you can speak more jargon or more abbreviated texts and the audience will understand that? So when you make the map, think about who you are targeting in making the map for. Don't intentionally lie with data. That's a big one. Statistics are great for lying with. So you can make a map in any kind of way to say anything you want, but don't make it lie. Be truthful and let the data speak for itself. Always show all relevant data whenever possible. Data should not be discarded simply because they are contrary to the position held by the cartographer. So again, that's kind of intentionally not lying with the data. At a given scale, strive for accurate portrayal of the data. The cartographer should avoid plagiarizing, report all data sources. So if you look at lots of maps on the bottom of the map, you'll see where the data was from. Again, it's kind of nice. If all the data is reported, you should be able to reproduce the same map the original author did. Symbolization should not be selected to bias the interpretation of the map. So for example, if you're having maybe mapping factory locations, you wouldn't want to maybe put skull and crossbones there saying, oh, these factories are pollutant and they're killing us. That's going to be biased. So it should be neutral and the data in the map should speak for itself without biasing the information in the reader. The map results should be able to be repeated by other cartographers, which kind of goes along with not plagiarizing and reporting all your data sources. So this turns us back to this question that we had discussed earlier in the semester. What's a map? So quickly, while there are many points of view of what a map is, here we'll define the map as a spatial representation of the environment that is represented geographically. By representation, I mean something that stands for the environment, portrays it, and it is both its likeness and a simplified model of the environment. Maps should do something meaningful, such as tell a story, present an idea, or showcase a situation. All maps are made with some kind of purpose. Fundamentally, maps display only two types of data: qualitative and quantitative. Qualitative data differentiates between various types of things, while quantitative data communicates a message of magnitude. So the map on the left is quantitative data, because it is expressing the magnitude of groundwater storage. So there is a number or a value associated with this map. It's a statistics map. So the map on the right is qualitative data because it is only showing types of things, and there are no associated numerical values. So nominal, categorical, and ordinal data are all qualitative data types, meaning that there's no numerical data or statistics about it. On the other hand, ratio and interval data are quantitative data, as they have a numerical or statistical value associated with it. So, okay, which two of these maps represents quantitative data? Well, the map on the left is quantitative data because there is some numerical value associated with it. And here we are looking at drought severity. So the darker the yellow-orange, it's extreme drought, and to the darker green, it's extremely moist. So that is a quantitative data map. While the map on the right is qualitative, because all this is showing us is these different types of soils, but it's not saying any kind of magnitude. It's not saying the percentage or how much of it there is. All it is showing you is this where this kind of soil can be found. Nothing more, nothing less. No magnitude, no statistical value can be reported. So recall the two different types of maps. There's reference and thematic. Thematic maps are meant to show attributes or statistics about places, spatial patterns for those attributes, and relationships between these places. Therefore, thematic maps map quantitative data. And so there's a variety of different thematic maps. For example, choropleth, dot map, proportional and graduated symbol, isoline maps, cartograms, and flow maps, just to represent a few. And we'll take a look at each of these in the following slides. So the first is a choropleth map. And choropleth mapping is a common technique for representing enumerated data. So these are maps where enumeration units, such as states or counties, are shaded a particular color depending on that unit data value. So here in this illustration, we have a enumerated area represented by polygons. And each polygon, as is seen on the left, has some associated data value. So from this data, we can then shade the polygon based on classification schemes, which is shown on the right. And generally speaking, the darker the color, the more of something there is. The lighter the color, the less. That's not always the case, but generally speaking, that is the case. So here's a choropleth map that reveals patterns within data by showing the distribution of the chosen phenomena within these selected areas. So in this example, the unemployment rate by county is being mapped. And notice that the map uses unemployment rates and not the total number of unemployed people. The use of proportions or rates instead of raw counts is fundamental in creating a proper choropleth map. If the map above used a raw count of the total number of unemployed people in each county, it would be subject to bias introduced by the size of each county. So larger geographic areas tend to have more people by virtue of having more space for people to live in. So using raw counts would show that. So unemployment would seem higher in large counties, not because unemployment is more common there, but simply because there are just more people there. That wouldn't make a very interesting map, or it wouldn't make a very informative map. So choropleth map should be normalized. The process of normalization accounts for differences in geographic area by converting the raw counts to rates or proportions. So population density is a great example of normalized data. It represents the number of persons per unit of area, often in square miles or kilometers. So here's an example. These are in Toronto, Canada, and these are census tracts that we can see highlighted here. And census tracts have between 4 to 6,000 people per census tract is what they try to keep the range in. And here's the underlying data, and we can see the numbers of people. And as you can see, just kind of showing these numbers of people per census tract is not very useful, not very helpful. It's kind of hard to discern any patterns or any meaning in that. So what we can do in GIS, and again, this is kind of using ArcMap interface and not ArcGIS Pro like we'll be using, but it illustrates the point. Where here we can map population for 2011. So here's a choropleth map showing population for 2011. So is this a useful map or not? Here we can normalize this data, and we can normalize it by square kilometers. So here's a map with the same data by population per square mile. The map is completely different, right? Now we can see kind of down to the lower center, where it's very dark green, the population density is much greater. So you always want to normalize your data. You never want to make a choropleth map of just raw data, just the total number of people. And this is much more accurate because it's showing kind of where this darker green areas is actually University of Toronto, much more people there. So think about it if you're trying to make a map and you want to locate your business in the greatest populated density area, that will be where you want to be. So always normalize your data when you're making a choropleth map. Here is the same idea with a dot density map. And dot density maps are a simple yet highly effective way to show densities, differences in geographic distributions across the landscape. So dot density maps are easy to understand and at a glance shows us intuitively where things clump or cluster. So there are two basic different types. So a one-to-one dot density map, one dot represents one subject or count, and a one-to-many dot density map in which one dot stands for a number of things or variables. Example, like one dot is equal to 1,000 acres of wheat production. So here we have a dot map where one dot is equal to 1,000 people. It's important to note that in dot density maps, the placement of the dot is not exactly where these people live. It's just showing you the number of people in that census tract, for example. They could be clustered in a spot, they can be spread out. The dots are just randomly placed there by the program. So, note all dot density maps should be drawn on an equal area map projection. This is crucial. Using a map projection which does not preserve the size of an area will distort the perceived density of dots. So again, we have our census tracts, but instead we want to represent the data as a dot density map. Here we can go the idea that dot value is too high, where one dot is equal to 10,000. And why is this dot value too high? Because it doesn't really show you any of the information. It doesn't show you any patterns. It just looks like people are randomly living throughout Toronto. Here's the dot size is too small. The number of one dot is equal to 1,000 people looks about right, but the size is too small. It's hard to read. Dot size is too large because then you can't discern any patterns. It just kind of looks like splottered paint, kind of not very clear. And here's just right. One dot is equal to 1,000. The dot size is right. So this is just going to be a matter of just playing around with the settings. And this kind of shows a nice spatial pattern. So with a dot density map, we can quickly visualize the spatial distribution of data. So here one dot represents 25,000 acres being treated with commercial fertilizer, lime, and soil conditioners. So we can see areas where farming is great, kind of upper Midwest. There's probably lots of corn, soy. California, in the Central Valley there's lots of agriculture going on there as well. So dot density map gives you a great, easy way to visualize the data. In Idaho, I assume kind of down in there, southeast Idaho, it's probably all potatoes. So the next is turning to proportional and graduated symbols. So proportional symbols scale the amount of simple symbols proportional to the data value found at that location. So the larger the symbol, the more of something exists at that location. So the most basic method is to scale the circle directly proportionate to the data, so that if, for example, Toronto has twice the population of Hamilton, the population symbol for Toronto will have twice the area. However, you can also group your observations into categories or numerical ranges and create graduated symbol maps that may, for example, only have 3 symbol sizes corresponding to the categories of the city sizes. So proportional symbol and graduated symbol. And you can really notice the differences there by looking at the legends, which are in the lower right-hand side of each of the maps. So an isoline map, and we're probably all familiar with contour maps, is a map with continuous lines joining points of the same value. So iso means the same. So same line, meaning that a line has the same value. So whereas in green there, the iso line pointing to that line, anything along that dark line is going to have the same elevation. So examples of an iso line map would be equal elevation, which are our contour lines, which we have on all our topo maps for hiking, temperature, which are isotherms, and barometric pressure, which are called isobars. The next is a cartogram, and a cartogram is a unique type of map because it combines statistical information with geographic location. So cartograms, on the other hand, take some measurable variable, for example, total population, age of inhabitants, electoral votes, GDP, and so forth, and then manipulate a place's area to be sized accordingly. So in this cartogram, the population of each country is being mapped, and the area of that country is being sized accordingly. So what we can say is, quickly, China and India have the greatest number of people, the greatest population, where places like Canada have a very small population. And they do that by showing, there's no numbers and there's no values on this map, but what it's showing you is by changing the geographic area of each country proportionate to the population. So they make some pretty cool maps. So here's another cartographic map. After every election, people always come out and make cartograms. And this one is a cartogram representing the Electoral College by scaling the size of states to be proportional to the number of electoral votes. So as you can see, the red states, which are Republican, don't have many electoral votes except for Texas. So we can look at some of these, especially Idaho and Montana and Wyoming and stuff. They don't have very many electoral votes, and so they're quite small. California and New York, on the other hand, and Florida are huge. Finally, we come to flow maps. And flow maps are a type of thematic map used in cartography to show the movement of objects between different areas. So these types of maps can show things like the movement of goods across space, the number of animal species in a specific migration pattern, as well as traffic volume and stream flow. So the use of lines on a flow map is similar to the use of graduated symbols. The lines are varied in width to represent the quantity of flow. And in this example, the thicker the line, the greater the number of fighters going into Syria. So flow maps can be a great and easy way to kind of communicate information as well. So on that note, have a great day.